here in F, we see the 3e to the x inside of cos, and we see that the derivative of 3e to the x is also in the question. So it tells us we should do a substitution. And when we're substituting, we always make u that inside function. So u equals 3e to the x, and then we do the derivative, move the x over, and we get 3e to the x dx is equal to du. That lets us substitute into our equation and make our integral into something easy. So now when I substitute for the yellow, I can put u, and then for the 3e to the x and the dx, right, all of this gets replaced with the du. So it's important notation-wise that we're not only replacing the 3e to the x with a u, but we also have to replace the dx with something so that when we get our new integral, it's got a new variable, but the integral is integrating with respect to that new variable. So the dx says integrate with respect to x. The du says integrate with respect to u. Well, cos u is an easy integral because that's just sine. Sine u plus c, and then we can substitute back and get our final answer. And the beautiful thing about integrating by substitution or integration in general is you have the derivative to check. If you're like, I'm not sure I did that right, so I'm just off to the side here, I'm just going to write sine 3e to the x plus c. I'm going to find my derivative. Well, if I was doing my derivative rule, I have a chain rule. My outside function is sine. The derivative of sine is cos. Keep the inside the same. Then multiply by the derivative of the inside function. And then, of course, the derivative of c, just because it's a number, will be plus 0. You don't need to write that plus 0. But I'm just showing you that it would go away. Does this match up perfectly with what was in our integral originally? Yes. So then we know that we have done it correctly. So on a basic level for integration by substitution, and you know, of course, that the AP course is going to definitely go beyond basic level questions. That seems to be a pastime of theirs. How difficult can we make a simple concept? And ask you questions about it. But on a basic level, what we're looking for is a function inside of another function, because that's the basis for the chain rule. And if the derivative appears, which it does in this situation, then we can use substitution. So G, again, a fairly straightforward one. I notice the tan is inside of sine. And I know the derivative of tan is secant squared. So my derivative is showing up. This one has a typo. Please add the dx there. Because without that dx, this integral really means nothing whatsoever. So I do my substitution. I let u equal tan x. I know the derivative. I multiply both sides by the dx and get secant squared dx by itself. Everything substitutes really, really nicely. And the integral of sine u will be cos, positive or negative? Negative. Negative cos u plus c, and then you substitute back. And we get our final answer. Now, each of the ones we've done so far, the substitution has just worked out so nicely and so beautifully. That doesn't always happen. Okay, so this next one, first of all, what makes the next one kind of awkward is that I don't really have one function inside of something else. I just sort of have two functions multiplied by each other. technically, there's a 2x inside, but a 2x is an easy derivative because it has a chain rule where you have to multiply by 2, so the opposite is just divide by 2, so that's not really, you don't need substitution when you have an ax plus b inside, because it's just simple, right? So I'm a little bit of a loss what to do, so I think, well, what if I made u the sine 2x? Because what's nice about the sine 2x is the derivative shows up as cos 2x, sort of. Right? Because if I take the derivative, I'd have a chain rule. And there's an extra 2. That's not in my original equation. Right? If I am going to, and I'm going to color code things here, if I am going to replace u with sine 2x, that gets rid of all of this. But I have a problem that I want to replace this with cos 2x dx, but if I move my dx over here, it doesn't match up perfectly. So I can't just replace the orange with du like we've done in the past, because things don't match up perfectly. But you guys are great at your algebra skills. It's not hard to match it up perfectly. They're sort of like, well, if I move the dx over to this side, and I move the 2 to the other side, and you see that this matches up perfectly if I have a half du. So this is our first question where we had something not match up perfectly. But with your algebraic manipulations, now I can say I can replace the sine 2x with u, and I can replace the cos 2x with a half du. Now that half is a number. It could be written as half of u. Integral properties say if you wanted to, you could put that half out in front. We have some choices. Okay? I just went right away to keeping the half out in front and just doing a regular integral. How do you integrate just a single variable? Add 1 to the exponent and divide. So I would get u squared over 2, and the half times the 2 on the bottom would give me a quarter or a 4 on the bottom of my denominator. And now I can substitute back in, and I would get sine 2x all squared plus c. Of course, you could also, no problem writing this as squared in there like that. Now I'm going to mess with your brains just a little bit. Okay? We're not done this question. We're going to do this question 2 more times with different substitutions and different techniques. Okay? So I'm going to draw a line here. This is perfectly fine. But I'm going to do it a second time, and I'm going to let u equal the cos 2x instead of the sine 2x. So 2 people said, oh, I chose my u differently, but it worked. Oh, this would be great on a take-home quiz, because I love listening to you guys argue. Right? You get into the, no, I got an answer, no, I got an answer. And then I even have people coming here and saying, hypothetically, what if you did this? And then if I say it's wrong, they're like, I knew she was wrong. It's like, was it really hypothetically? Right? But that's what happens sometimes. I love your guys' arguments. So, somebody else does let u equal cos 2x. Well, then du dx. Now this is the derivative of cos. It's going to be negative sine 2x. We have a chain rule. So we'd also have a multiply by 2 at the bottom. And when I multiply the other side by dx, I'm going to have to move the 2 and the negative to match up perfectly. So my integral, the cos 2x becomes u. Maybe I'm going to just zoom out here for a second. I'm going to go back to my original one and do some color coding. Right? If I make u the cos 2x, then this part is going to get replaced with a u. Does that make sense? And then I'm left with a sine 2x and a dx. And in rearranging my derivative, the only way I would get a sine 2x and a dx is if, I'll circle this in red, right? The sine 2x dx is if I had a negative 1/2 u. So this part, well, that's color-coded nicely. Like it was separated in the original question, but that whole red box, now that is going to get replaced with negative 1/2 du. I can integrate this because it's a simple one. Add 1 to the exponent. My negative 1/2 would just be out in front. Add 1 to the exponent, divide. And substituting back in, I get negative 1/2 cos squared 2x. Oh, maybe I'll put the 4 on the bottom. Because 1/2 times 1/2 is 4. Just have the negative up front. Plus c. And in the first one, I got this as a final answer. And in the second one, I got this as a final answer. And they're different. And they're not identities. They're not even, like, sometimes you get different answers. Oh, I got a half. No, I got 2/4. Right? Okay, you guys are arguing the same thing. Right? But this is different. And if you graph them, they're not the same. It's not the same. It's sort of a little messed up. But both answers are right. Oh. I don't know if that bothers you. That kind of bothers me a little bit. Kind of like, what do you mean? You get 2 different answers and they're both right. That feels a little bit wrong. Okay? Oh, but maybe there's a different plus. I don't know. It's kind of, it's worth thinking about. Because it should sort of bother you. And now, what I'm going to do is keep messing it up a little bit more. We're going to do the same question. But someone says, oh, I came up with a different idea. This is what I came up with. I had my sine 2x cos 2x dx. And I was like, oh my goodness, that is so close to my double angle identity from grade 12 trig identities. And since I have them memorized so well, I recognized it right away. The only problem is it doesn't quite match up. It doesn't quite match up because I would need a 2 here. Right? Then it would match up perfectly. I'll show you a nice mathematical trick. I'm going to add the 2 and add a half. Whew. This is actually a really important higher level math strategy. Doing something that does nothing is the strategy. What did I do when I added a half and a 2? I multiplied by 1. I didn't actually do anything to the equation, but now this is so nice because it matches up my identity perfectly. So I'm going to still have the half, but now I'm going to change this part, right, to sine 2 times 2x, 4x. And now I don't even need substitution. because this is a simple integral with a simple chain rule. Simple chain rule where you have to multiply by 4. When you integrate, you just have to undo that and divide by 4. So what would give me this? This will be negative 1/2 cos 4x, and I'd have to divide by 4 plus c. So I get negative cos 4x over 8 plus c. Completely different function than the first two. Again, I would suggest playing around with these, graphing them, seeing if they look, are they exactly the same equation? Do the graphs show up to be the same? Ah! Okay. This is something that I expect to see AP classroom, AP exam doing a lot. Being like, oh, you can use one of your trig identities to make this nicer. If you use one of your trig identities, then you can integrate nicer. Okay? You will also start to see substitution ones like this at the top, where initially the derivative doesn't match up perfectly and you have to do a little bit of manipulation. So when you substitute in, there's going to be like, I had an extra half here. Not a big deal, but a little bit more of a challenge. Right. So, again, now I'm going to get you to work on some. This one, also, when you do the derivative, doesn't match up perfectly. But let's see if you can manipulate things to make it work. Okay, so we've got our u's 4x squared plus 1. It's easy to see because it's inside of e. That's a good place to start. When you take du, you get the extra 8. So you have to divide by 1/8 to just get x dx. Now our substitution for this then becomes this. So now, I mean, I rewrote the original one with the x dx second, just so that things were clumped together nicely for substitution. Not necessary, but I just, visually, I like that. So now I have e to the u, because the u gets replaced with the 4x squared plus 1. And the x dx is 1/8 du. Now that 1/8 I can bring out in the front. I can just leave it out in front. 1/8, what's the integral of e to the u? Still e to the u plus c, and then we can substitute back. Again, you see the 5 minus 2x to the 4 is inside a square root. That seems to be a good idea to try for you. We take our derivative, and we have an extra -8. So we bring that -8 to the other side. And when we rewrite it, okay, first of all, I rearranged it here so it really nicely fit my substitution. You don't have to do this, but I changed the square root to a -1/2 because it was on the bottom. Now I have my u to the -1/2, and this part is -1/8. I'd probably even like to put that in brackets, just because sometimes when you write a negative, your brain later on looks back and thinks it's a subtract sign. So the brackets are nice. Now integrating this is no problem, because you would go -1/8, you'd add 1 to the exponent, divide by 1/2. That simplifies the -1/8 divided by 1/2 to a -1/4. Substitute back. Oh, I see some happy faces. You crushed it. Okay.
I actually did it.
Right? Now, these ones where it doesn't quite match up, you can see why just trying to do the reverse chain rule in your head becomes tricky. Because there's so many little things you have to remember with the chain rule that it would be really easy to screw up if you tried to do this one directly. Some of the early ones, that we did, I think you could have just looked at and written down the answer and been fine, and that's great. But when the chain rule isn't perfect, then substitution lets you solve it nicely. So the 4x cubed minus 1 is on the bottom, so we make that our u. Now when we do du, we get 12x squared. A couple of things you could do. Either, okay, sometimes I have people just get the x squared dx by itself by dividing by 12. And then when they substitute in, they would say, well, there's still a 5 there. That 5 still has to stay there. And some people say, well, if I want the 5 there, I just have to multiply both sides by 5, and then I have the 5 there as well. Either way should give you 5/12 in the original equation. Again, if I rewrite this so that things match up nicely, I have a minus 1 there. Excuse me. I have a minus 1 there. And I substitute in, and I get a u. And then I've got my 5/12. So whether you substituted in the 1/12 and kept the 5, or substituted in the 5/12, they both give you the same thing. From here, you have to recognize the natural logarithm. Oh. Right? That breakfast purple sheet that's on your purple sheet, u to the minus 1, 1 over u. You need to recognize that as natural log. How many people added 1 to the exponent and were like, and I got a 0, and I'm like, what do? I don't know what to do. How many people added 1 and added wrong and were like, oh, I just got minus 2, this is fine. That happens too. And so now we substitute back in. This is the strategy. If you let u equal the inside part, and we solved this the other day using a different strategy, but I'm going to show you this strategy as an easier way of doing it. If you make u the inside function, then du is just 1. So du would be dx. But I can take this and rearrange it and say x would have to equal u minus 4. And I have a different way of substituting. So now I would have, instead of x, u minus 4. And instead of square root of u, I have square root of u du. And I can multiply that out and get it into a form that's nice. Daniel, you should compare this with the method that you did.
Oh yeah, I looked at it after and I was like, oh, I'm so stupid for not thinking of this.
No, this is not. No, this is not. This is. This is an idea that's completely new that we haven't seen before. So why would you think of trying to do that? You're always trying to get rid of that x with your derivative, but your derivative didn't do that. But rearranging, now we have something where we can take the integral, add 1 to the exponent, and divide. Five halves, 3 halves, 3 halves, 5 halves. Why are you saying that this little blob does not look like a 2?
It does look
It looks like a blob.
It does look like a blob. I think it's really blob-like.
I didn't like it. What's it called?
And then we substitute back in. So that could be another strategy. You take the u and make it the whole square root and see what happens. I like this method best. But it's a new technique. So, this idea is different than the other ones. It is a new technique where we had to rearrange in a different way to get rid of the x because the derivative still left us with an x. Okay, we will end there for today.